All right, guys. So we are going to continue with the second half of today. So let me share the screen here. All right, so the audio is on and it's recording, right? It's recording. All right, so let's continue then. So we were looking at in part one of the class today in the first video, right? We saw the code for CIFAR. Here it is, CIFAR10. So what is the CIFAR10 data set? How to use Torch Vision, how to download it, how to look at an image, how to basically look at the shapes of the image, and then basically we started looking at transforms. Okay. And this is a transform. We've seen how we can apply it to the entire data set. Now, the next step is, well, as I've said many times in the class before, whenever you do machine learning, deep learning, it's very highly recommended that you normalize the data, right? And there's a whole bunch of ways of doing that, whole bunch of libraries. Today, we're going to look at yet another way of normalizing our data. All right, so I'm gonna proceed to do that. So let's put in this section, let's call it normalize. And if anything, nowadays, there's just a lot of ways of doing everything, okay? But at the end of the day, normalization is about taking our data set, right, and transforming it. Hence the name transforms, right? We're gonna transform it. So it's very much like, sigmoid functions or logarithm, right, that we're all familiar with. Any kind of function transforms a data set into another scale or range. In this case, the objective is going to be, we saw the data in the previous video, and we saw that it was from 0 to 1, right? We saw that the minimum was 0, the maximum was 1, right? We looked at the tensor data. What we want to do now is we want to even change that further, right? So we're going to transform the data or normalize it so that in essence, the data is zero centered, right? So we're going to put it in like a scale where the center is 0, and then there's some kind of a standard deviation, okay? So we're not going to really even look at the equation for that. We're just going to rely on the normalize function basically provided in the transforms module. However, just keep in mind, you can also write equations for a lot of this, right? So you can write the equations at some point later in the semester. We'll take a look at one of the equations. But in particular right now, because we're just really interested in the applied part of this, we're just going to look at another one of the available functions for doing this. So I'm kind of going to start at the very end, and I'm just going to say here, temp as in temporary, right? Transforms. All right, and this is going to then call from the transforms object, we're going to call the normalize function, okay? So we're going to call the normalize function. So the normalize function takes in two things, all right? Takes in two things, which are the mean and the standard deviation, right? So it's basically like any normal distribution that you've learned about in your statistics classes. There's the mean and the standard deviation to define it. So here we're going to need to calculate it, but here we provide them. So we can call this whatever we want. So let's actually call it, mean info, let's say, comma, and let's call the other one, standard deviation info. Okay, just provide this with some parameters. So that's what the equation wants, right? So we need to actually calculate this directly, and then we just plug them in the function. All right, and then if we want later, we can actually view this function itself. So I'm going to say temp transform. Right, now the question is, how do we get this information, right? So let's go over here. And basically what we want for this normalization is that we want it to be, we want to make all the data to be transformed to be zero mean, okay, with standard deviation. Okay, with as defined by the functions themselves. So here, you know, we have to think a little bit about this, all right? How are we going to proceed with this? So we have to think, okay, we have a lot of data, right? We have a lot of data. We want all the data to be, you know, have a mean and a standard deviation, and we want it to be normalized. So we have a lot of images. We have, let's say, 50,000 images. The classes don't really matter, right? The dimensions, you know, don't really matter because it's all within that scale. Let's imagine grayscale. But the thing that could matter is the RGB. Do you guys see that? There could be a pattern of data for red versus a pattern of data for green versus a pattern of data for blue. Do you guys see that? We could, in theory, normalize it across all channels also, right? We could just take the mean and the standard deviation out of all images. That's possible. And it should be fine, I think. But there are three channels, right? Red, green, and blue. It could be possible, for instance, if we think about this instinctively, that in a world, in the real world, greens are what? Darker. Blues are what? Lighter. Reds are very bright. I don't know. So, do you know what I'm saying? So my point is they're not exactly the same, right? Whereas greens might be really bright or really strong, blues may be very light. You see where I'm going with it? I don't know exactly the real world, but I'm saying there's differences across those three channels. Do you guys see my point? So we could certainly calculate this standard deviation and mean across independently for the three channels. So basically we do three of these and then apply each individual one to the appropriate channel. Do you guys see that? And this can be done efficiently. The thing is, we have to be extremely careful in the dimensions. Do you see where now we start to get into the tensors? Now you really have to think about the dimensions, because when you perform multiplications, you want to perform them correctly. Do you guys see what I'm saying? And this is where it gets real and it gets tough. Okay, this is where now you see both the power of something like PyTorch, but also the complexity of getting this right. That in one single operation, very efficiently, you can accomplish what you want, but at the same time, you have to be very careful about it. Make sense? All right, so that's what we're going to try to do. So we need to think about this a little bit. All right, so let's first, we need to calculate mean info, right? And I just want to make sure that I'm recording. Yeah, I see the volume moving. All right. So we need mean info, and we also need standard deviation info, right? So we need to figure out what these are going to be. We can print them out when we're done. I'm going to do print just to see what's in there. Standard info print mean, right? So we can print those out. right, so we know that this will give us the transform that we want. It'll normalize it. We just need the information about the mean and the standard deviation. So we're going to calculate that directly here. And so the first thing that we need to think about is, so now let me actually comment all this out. So I'm going to comment all this out. And what else do I need? I need to now, obviously, I need to take all the images and put them together in some kind of a tensor, right? So I have currently tensor CIFAR10, which is basically a data set. We got the length of it, right? It was 50,000, I believe. And we've got all the images there independently. We can use the square brackets to get them. Now we need to create one single tensor, right? Which will probably be pretty big. 50,000, it's actually 50,000 by 3 by 28, 32 by 32, somewhere along those. So we need to create that tensor. So let's try to do that. So I'm going to do IMGs. Notice now it's images, right? Torch dot stack. So we're going to actually try out the torch stack function. So let's open up the browser and let's look for that one. So this is going to be part of everything that you do, right? So figuring out how to do these. So this is going to be torch dot stack. All right, so we're going to look up that function. Okay, so the torch.stack function basically concatenates a sequence of tensors along a new dimension. Okay, basically that just means we create a new tensor. You know, with a new dimension, all tensors need to be of the same size, which is perfect here for images. It takes in tensors and you specify a dimension over here, right? So let's see what that, oops, sorry. So tensors, sequence of tensors to concatenate, dim in int, dimension to insert has to be between 0 and the number of dimensions of concatenated tensors. Okay, so we need a dimension here. So let's take a look at an example of this. See here, you specify 2 and then you end up, I think, with 2 here. Ah, no. Sorry about that. All right, so let's look at another example. Kind of a big one. Just looking for something simple. That's the same one. So this is a good example here. The images are 2, 3 by 4, right? You guys see that? So this basically becomes 2, 3 by 4, and then here we just have Okay, you guys see that? So that's a good example. See another example. Stack this one, dimension 0. So, all right, let's take a look at this one. All right, so I think that's enough. Let me go back to the definition. Dim just means dimension to insert. I just want to make sure about the dimension. I'm a little... So if we say dimension 0, right, stack function, stack operation also joins a sequence of tensors, but over a new dimension. Moreover, they have to be of the same size. Okay. Great. Okay, so let's try it out then. All right, I'm going to close this. All right, so the idea then is we need to create one single tensor. So I'm going to use stack here. All right, and then I need to provide two parameters, which are all the tensors that I want to stack together, and then a dimension parameter. So we'll play with that a little bit, I guess is the best way. So dim equals 0, and we saw in some examples, we could put in 0, right? We can put other dimensions in there. So we'll take a look at whatever the output is. So then we'll need to print images.shape to kind of get a feel for what it is that we want to do. So in this case, we need all the images, right? So stack all tensors returned by the data set along some dimension. So this is a list of the images. I need to get them from the data set. So I'm going to do a list comprehension. And I'm going to say for imgt, comma, label in tensor, CIFAR10, right? So that should be clear. And then out of this, the list will just be populated by image T. So on here, I need to put in image T. Remember, this is a list comprehension. Whatever would go under the for loop goes now before in this approach. So image T. This same image T just gets added here without any transformations or anything like that. And that's a standard list comprehension. So image T, for image T label in Tensor, CIFAR10, all right, and then dim 0. So that should do it. That will stack them together, right? This is going to stack them together. And then we specify, we saw in some examples, we could do dimension 0. So let's now try this out and let's just see what the shape of IMGs is to see if it'll meet our needs, basically. Should be the last thing that gets printed out. Let's try it out. Okay, so some information there. Now I do have, I'm going to remove those, that data. I'm going to remove these. I don't need this anymore. Okay, so I'm going to run it again. All right. Okay, so basically I created a tensor of 50,000 images, right? And then it's got 3 by 32 by 32 because every image is 3 by 32 by 32, right? That's the standard shape of an image. They all need to be the same image. And then it just created this dimension of 5,000. So let's play with this a little bit. And now let's see what happens if we try to add dimensions to this. So let's do, let's try another one. So let's add dimension 1. So in this case, it's 3. So before it was 5,000 by 3 by 32 by 32. Now it's 3 by, or 50,000 by 32 by 32. That gives us something, right? So you probably, what do you guys think happened? What would you suggest? There's a way to test this, right? So that's where I was a little bit confused when I was reading the description. It almost seemed like it's permuting. So let's try it again. So now I'm going to do 2 here. Okay, this one is 3 by 32 by, it's shifting to 50,000, right? Which is fine. So this is interesting because if you think about this, when you think about tensors, you can almost think of them as a Rubik's cube, right? You guys remember Rubik's cubes, right? And tensors follow that same idea. You're just shifting the Rubik's cube. The data is still the same, right? It's still the same cells. Nothing has changed or been added. You're just, doing that whole thing with the Rubik's cube to move it around. All right, and that's kind of useful. And this is what I was saying before. Remember, what we may want to do is normalize across all data and all channels, or we want to normalize across all data but have individual channels, like the red, the blue, and the green. You guys see that? And that's the trick here, is that if we just want to retain some of the channels, we'll have to play with this. So let's try it one more time just to kind of corroborate our inclination here. Let's do dimension 3, right? So this should have shifted the 50,000 all the way to the end, hopefully. Aha, and it did, right? Do you see that? So again, the Rubik's Cube, still the same data, we just shifted it and moved it around. And so now we've left it as 3 by 32 by 32 by 5,000. And what's important here is we have the 3 channels, I suppose, in the front, the red, the blue, and the green, okay? So we've got all the images stacked. And we have basically 3, 32, 32, and 50,000. So it would make sense now that the 32 by 32 by 50,000 can be normalized across the 3 channels, red, blue, and green, if you think about it. Do you guys see that? Because we need to grab a mean and a standard deviation for it. So let's try that. You just got to figure it out then. So let's go back to the code. So this moved it a little bit. We've got the shape now. All right. So now, so we've created one single tensor where we have the channels in front. Okay. Now we want to compute the mean and the standard deviation. Okay, so now the next step is compute the mean and standard deviation. So we need to think about how to do that. And because we have shape, so the shape was 3, 32, 32, 50,000, correct? Guys, this is what we had. So basically, what we want to do is we almost want to say it's 3 by this whole thing, because it doesn't matter. For every image, for every 32 by 32, we're just going to make it into one single thing. You see that? The 50,000 is like we can make it into one single vector, if you will. So 32 by 32 is what? What is that number? 32 by 32? What? No, what is that number? Like, what does it come out to? So 32 by 32 is 1,024. All right, 1,024. So this is 1,024 by 50,000. Whatever that number is, now it's going to be a 3 by that vector. 1,024 by 50,000 is pretty big. But then we're just going to take the mean and the standard deviation for all of that. Got it? Let's see what happens there. So then we want to go. So as I said, remember, this is the power of tensors and torch, but this is also where the complexity starts to come in. So then we want to do, we need a way basically to convert. So convert. So let's say convert this to just basically 3 by whatever it is, right? Something like that. So then, and then we can take the mean and the standard deviation overall, right? In a very quick and easy computation. That's extremely efficient. So to do that, then let's go back to these now. So let's go back to these. So mean info will be images dot, and now we can take a different view of the data. Right? Taking a different view of the data is basically sort of transforming it, not transforming the underlying data in memory, but just transforming a version of it that we can process. So as it turns out, there's in both TensorFlow and PyTorch, there's an operation, and NumPy, there's an operation where you can say, okay, you have something of size, let me do this, 3 by 32 by 32 by 5,000, infer that into 3 by whatever. And to do that, you can just say -1. The 3 will be maintained because that's the first one, and then the -1 just makes the rest one single thing. And that's a very common thing that you'll see can be applied to everything. Now we have this tensor, right? So let's just actually, for the sake of argument, print it out. I want to be double 100% sure here. So mean info dot shape. I'm going to do a print mean info dot shape. All right, should be a tensor, so that should work. Okay, so what was it? 1024 by 50,000. 512 with 5 zeros. All right, perfect. So it worked, right? Our intuition was correct. So you can see this exercise is actually a good one because, as I said, it shows you the power of, but it also the complexity of it. And this is a lot of what you're going to be dealing with in deep learning, right? If you want to write, you can't write code now with for loops and things like, you got to write it like this. This will execute really quickly, but it's, you know, a bit tough to figure out. All right, so now that I have this, that's perfect. And now I can, you know, get rid of this shape here, and I have the tensor that I want. Would you guys agree? We have the tensor that we want. So now let's just go ahead and calculate the mean of it. Oops. I'm going to say dot mean. Now there's another problem. We don't want the mean out of all 3 channels, right? We want the mean for each channel. So the red should be a mean, the green should be a mean, the blue should be a mean for the 3, right? So all we have to do here is specify the dimension across which we want to perform the operation. So in this case, the dimension should be, how many dimensions are in this view? 2, right? Where if we applied it to 0, it would be over the whole thing. But we just want it on the second dimension, right? So that's 1. You guys see that? Does this make sense? Are there any questions about this one? Nope. All right, perfect. And that's it. You see how efficient this is? This is the beauty of TensorFlow, or sorry, PyTorch. All right, so now we have that one. Yeah, go ahead. Yes, that is the intention, yes. Got it? Which is what I was saying. Intuitively, just think about it. Reds might be brighter, blues might be lighter. So they shouldn't really have the same distribution of the data, right? See that? Yes. All right. So now that we know this one, it should be pretty easy to do the other one. Get rid of this one. Now we can do the exact same thing for standard deviation. So we're going to take IMGs dot view, another view of the data. 3, because we want the 3 dimensions. We infer with -1 the other 3 dimensions into 1, and then we do dot standard deviation. And again, we need to specify across which dimension. So in this case, it'll be 1. That should be a 1. And that should do it. Now we have the data that we need that will be applied correctly to our tensor across every single one of the 3 channels. And everything else was already done for us. So we have here stacking the images. We have here the calculation of the mean, the calculation of the standard deviation. Let me get rid of this because this will. And then here we have the normalize function, which basically just takes in the 2 parameters. And now we have our built transform. So now this transform can be applied to our original data set in order for us to arrive at a normalized data set. Perfect. Are there any questions, guys? All right, good. So now that we have this, let's go ahead and download the data set again, but this time around with all the transforms, right? So that we can easily then, not even have to worry about it. So then we'll do, now we're going to repeat the exercise of downloading, but we're going to give it yet a new name. This time we're going to call it transformed CIFAR10. All right, so transformed CIFAR10 just means with the transforms, which means it's tensors, it's normalized, all that. So it's going to be data sets dot CIFAR10 data path, comma, train equal true, because this is the train set. And correct me if I'm doing anything wrong. Download equal true. You can make this false at this time because we've downloaded it many times. Just be aware of that. And then down here now, we're going to provide all the transforms that we want. So we've got the transform parameter equal, and now we can compose a transform. So we can use transforms dot compose, right? And here we're going to specify all the transforms that we want as a list. You guys see that? So then we can just move this down here, closing brackets. And then in this line, we're going to plug in our transforms. So what are the transforms? So the first one was to tensor. To tensor. Oops. And then the next one will be the temp transform, although we can just write it directly. Normalize. And then it's going to take mean info, comma, standard dev info. And that's it. You guys see that? All right, for the validation one, we can just copy this one. Okay, so this, we're going to call it transform, but now it's going to be CIFAR10 validation data, or the test set. So data set CIFAR10, data path. This train will now be false because it's not the train set, but the other one, the 10,000. Download false, we already have it. Transform equal transforms dot compose, which is composed of a transforms to tensor and a transforms normalize. So I know it's a lot of processing, but it's the most efficient. If anything, think of it that way. If you had millions of records, this will be pretty fast. Got it? Are there any questions? And this is just, you know, a little bit, right? There's a lot more. We saw there's a lot of transformations. There's a lot that you could have a list of 20 transformations in there if you want. You could blur the images. You know, do all kinds of things. Make, you know, whatever you want. All right, perfect. So that, let's run this. Let's make sure it runs. So let's run the code. And there it is, right? So you can see that when this prints out now, you know, you got some data for the mean. These are the means and standard deviations that we calculated, right, for RGB that we're applying basically. And that's all of our data. It ran correctly. We've got the done here, so that means there were no errors. So now we have our data normalized. So we can go back to the script. Okay, and now we proceed to do some more work. So now the next thing you might want to do is you might want to view the images. Remember, this time around, the images are no longer the original ones, but they are the normalized versions of them, but we can still view them, right? So let's think about that. So let's print out the normalized images. I'm going to do print here normalize image. It's just an example. So again, img t label from transformed CIFAR10. Right, so we're going to grab, you know, one image from the transformed CIFAR10 data set, and we're going to view it. Keep in mind, they are channel height width, so we have to permute them again. I'm going to do plt dot imshow of img t dot permute and once again 1, 2, 0. We're moving the 0 to the end. All right, and then we're going to do plt.show like that. So now this should be the normalized version of the image. So let's take a look. You guys see? You see that it looks a little bit different? What in particular looks different, would you say? The background, right? The background just became like dark, which is good. It'd be, that actually by normal, even intuitively, even though the algorithm does better for other reasons, even intuitively, when we look at this image, we'll say, oh, well, the background won't confuse it that much anymore, right? Even intuitively. So yeah, good. All right. It's more obvious that the car has some reflection from the sun or something. So that's good. All right, great. So we can see that we can normalize the data, but we can still view it, and that's pretty useful. So now we're basically at this point ready for the modeling part, The only thing is we need to now, if you notice, I've been ignoring the labels quite a bit, right, in the past because we were so concerned with the data itself. But now, of course, we need labels, right? So now keep in mind, everything that we've done before in the previous class was linear regression, right? And remember that linear regression is mostly about like the intuition, right? And linear regression has applications, obviously, very important ones. But in this case now, we want to do classification. So basically, we want to have images of whatever, cars, trains, etc., dogs, I think, and we want to be able to classify. We're also going to keep it simple, so we're not going to look at all the labels. We're just going to take 2 labels out of the 10. Okay, so let's do that conversion. And to do this, we're going to use a list comprehension from the normalized data, and we're going to create our data set basically. So let's do here. Let's call this one building the data set. Building the data set. And let's just say using only 2 of the 10 classes, right, from CIFAR. So we're just going to use 2 of the 10 classes, not all of them. All right, so how do we do that? Let's say, questions? All right, so we're going to do a mapping. So let's create a label map first. So label map, and the label map with curly brackets, we're going to say, okay, we're going to map label 0. We're just going to have 2 labels, 0 and 1. Guys, 0 and 1. But we're going to use the real labels 0 and 2. All right, so the real labels 0 and 2, which should be airplane and bird, I think, according to my notes. But we're just going to map them to be 0 and 1. Okay, so that's why I'm going to say 0 will map to 0, right? Pretty straightforward. But label 2 will map to 1. Okay, so that's all I'm doing here. And we just for reference, I'll add in here that the class names, we won't really use this, but just for your own knowledge, should be so one is going to be airplane, right? And the other one's going to be bird. To try to distinguish what's, in an airport, for instance, right? If you wanted to build a system that's looking at the sky, well, sometimes a bird could fly really close to the camera, looks big, right? Or a plane is, up, obviously, hopefully not so close to the camera, right? And so you want to be able to distinguish between the two. All right, so in that case, then we have airplane and bird here. So now the question is, we want to create the data, right? So let's say CIFAR, just some other name, 2, and CIFAR 2, CIFAR 2, but this is going to be the validation. Okay, so we've got the data here. So now we're going to just grab our data, right? We're going to use a list comprehension again. So I'm going to say for IMG label in transform in transformed CIFAR10 if label in 0, 2. All right, so if it's only when the label is 0 or only when the label is 2, will I grab this image? Okay, guys? So from the transform CIFAR10, and then I have the image. And so then here I'm just gonna create like a tuple. And I'm gonna say, well, the image, of course, comma, but then I need to map the label, right? So the label is gonna be either 0 or 2. I need to map it to 0 and 1. You guys see that? So very easily, I can just do that by using the label map and just plugging in the actual label. And that's it. So when I say label is 2, it's going to map to 1. When I say label is 0, it's going to map to 0. Got it? But we only do this for the ones that match 0 and 2. Any questions about that logic? Nope. All right, great. So now I have my data here. Next step is to do the same with a list comprehension here for image, comma, label in transformed CIFAR10, but this is going to be from val, right? If label, again, in 0 or 2. 0, 2. Right? Only if it matches those, then I'm going to add the data to my list as a tuple. It's going to be img, comma, and again, I use label map, and I just plug in the label. So again, if it's 0, it's 0. If it's 2, is 1. Questions? Nope, I'm not hearing any questions. All right, good. So now you have your data set, okay? You have your data set that we're going to use, and now we can proceed to building our neural net. So that's the next question. So let me save this. Let me run it actually, just to make sure it runs. Oh, and then we need to deactivate that. All right, and it executed correctly. That message there, clipping input data, is related to IM show, so I'm not so concerned about it. So let's deactivate this and that. All right, so now here, so we've got our data set with 2 classes. We need to perform some type of classification. All right, so we're ready then. So we're going to do here training. And then here we're going to do testing. Okay, this part in theory, you guys should be able to do it on your own now, right? Because it's very similar to what we did with the linear regression. So in theory, I encourage you to try to solve this on your own later, maybe, but I'll go over it So first, we're going to do the training part. So let's take a look at that. We have to build the entire neural net for this. So let's say here, training the model. Now the model architecture. We have to think also of how we're going to feed the vectors, right? So currently the data looks like this, right? 32 by 32 by 3, right? Or 3 by 32 by 32, regardless of how it is. That's what the data looks like. But what we may want is maybe, now if we were using CNN, we would probably keep it as a tensor, you know, like a cube. However, we're not, you know, the easiest thing that you can do with a vector is just spaghettify it, right? So, you know, push, you know, pull it. So 3 by 32 by 32 is actually what? If I want to make it into one vector, it would be 1 by what? Can you guys do that math? Anyone? $3,072, right? 3072. Perfect. So that's what we want to do, really. Okay, so now then we want to do that. We want to create these vectors. So let's start. So you guys already know a template to follow, right? You guys know already about template to follow to build an architecture, so you should follow it. But let's start putting in some of the variables that we know. The number of classes is 2, right? So we know that. So 2 classes. Okay. We're going to need to build a model. Okay, so we need to build a model. So let's see. So let's just build a model. Okay, let's build an architecture here. Model equal nn dot sequential right, like that. So now let's build the architecture. We saw that this is the exact same thing we saw last week. So nn.linear, right? We need to specify some dimensions here, comma. Remember that we want the nonlinear activation function. So we do nn.tangent. Later on, we can try other things like relu and h. How many layers are we going to have in this? Is it a neural net, deep neural net, right? So you have to play with that. For now, I'm just going to keep it simple. So this is linear. Right. Then here, I have to decide what function I'm going to use here. So this is where I'm going to, because we're doing classification, when you're doing classification, you want to introduce, so I'm just going to kind of say it now. Later on, we're going to see how it works. But we basically provide a new function for classification called a softmax. Okay, softmax. And that's only for the last layer of a classification problem. What the softmax does intuitively is that when you have whatever number of neurons in the output, whether it's 2 in this case or 10, it'll look at all of them, at all the values, and it'll make sure that all those values add up to 1, which is pretty good, right? Because if you're doing a probability, right, between two things, you want this to say 30% and this 70% adds up to 1. Or you want this to say 20% and this 80% adds up to 1. If you have 3 classes, you want it to say 10%, 5%, 85% adds up to 1. You guys see that? Intuitively speaking, that's what softmax does. Okay, and we just say the dimension here because it's going to be 1 because it's not the n number of samples, but just the next dimension. Okay, does this make sense, guys? So I just added, because we are doing classification here, I just added the softmax activation function. For the other ones, tangent, ReLU, sigmoid would be worth trying. All right, now the architecture. You guys should be able to tell me some of these parameters now. What are they? What's the first one for linear? Yes, and we said that we're going to spaghettify the data, right? To 1 by 3072. Do you remember that? That's actually written over here. So we need to do that for the data, but it's going to be 30 by 7, like that. 3072. Got it? What about the last one here? What would that one be? Number of classes, right? And the number of classes is 2, so that's n out, right? And we have it. And then whatever we put in here in between is really our architecture. Currently, we really just have how many hidden layers? We have 1 input of 3072 layer, 1 output of 2, and then what else? According to this, 1 more, right? Hidden layer. It's and we can define the size of it, whatever we want it to be. I'm just going to say 512. Remember that these two need to match. Does that make sense? Is this a deep learning algorithm? No, it's a multi-layer perceptron, right? If it only has 1 hidden layer, it's not deep. It needs to have at least 2 to be deep. That's it, right? So we built a very simple model. You guys know how to build. So basically, it's what we did with linear regression. The only thing is I threw in this softmax function in there. You see that? At some point, as time permits, we'll come back to play around with the softmax function a little bit more to get more intuition. All right, great. So I have the model built. That means I can literally right now give it vectors of 30 by 72, and it will predict. The problem is the weights in this architecture are currently what? Random, because we haven't done any training, right? Have we done any training? No. So we haven't, but we could predict something now. Okay, so maybe we can even try to do that. All right. So we've built this. So let's try to do something like that. So I'm going to say, let's say test the model without training. When weights are currently all random. Right, so the weights are currently all random. So but we can test it out. So I'm going to take IMG and label from, remember that now our data set is called CIFAR10, right? CIFAR10, because it's the one that's ready to go. So I'm going to grab one of those from CIFAR10. Let's grab the first one, let's say. And let's print the shape of it. G.shape. You can view it if you want, just for the, because we're running out of time. I'm not gonna view it. Okay. Now we can always change that architecture, obviously, so that's not a problem. All right, so now that the trick that we need to do is we need to, currently this image is 3 by 32 by 32, right? So we need to change that shape because we built an architecture that only takes vectors of 3072. Do you guys see that? And actually 1 by 3072 is what it's expecting. So we need to change our tensor to be of that shape, but already I've given you examples of that, so you should be able to do it. So transform from 3 by 32 by 32 to 1 by 3072. That's what we need to do. So how do we do that? Let's create a variable. Let's call it image batch. Keep in mind, I'm using the word batch, but currently it only contains 1, right? But usually batches will include several because they're tensors, they can be that way. So in this case, I take img, which is, this one, right? And I'm gonna use that view magic thing, right? So the view allows me to kind of modify it, right? So I'm gonna modify it. So I'm doing img view. And I'm going to so I want to convert it from 3 to 32 to 32. From 3 by 32 by 32, a 3-dimensional tensor, into just a 1-dimensional, right, of 3072. So how do I do it? -1. Remember, it'll figure it out on its own. However, there's a bit of a problem if we print this one, img batch. Right, if I just do that, dot shape. If I just do that, let's run the code. It's only 30 by 72. You see that? We need it to be 1 by 30 by 72, just to be a vector, 1 by 30 by 72. So how do we do that? Unsqueeze. I know it's like a strange thing, but it's extremely useful. All right, unsqueeze, exactly, perfect. All right, so let's go over here then, and now that's a tensor, so then we just do unsqueeze. Right, and we add the dimension there. So now we try it out again. And there it is. Now it is a vector of 1 by 3072. So it's starting. Why? Because remember, when just think of it this way, right? Think of it this way. We are always imagine that you're feeding into a GPU. Always, just assume, even though you might be feeding to a CPU, just think of it that way. So you really don't just want to give the GPU 1 image at a time. You want to give it 64 at a time. Right, so it's always going to be 64 by 3072. You see that? When you feed it into the architecture. Therefore, this one, there's only one, should be 1 by 3072. Make sense? 64 would just mean 64 images. Here we only have 1. But the dimension, it's got to be like a matrix type of a thing. All right, perfect. So that's done. So now let's scroll all the way down. All right, so we did this one. It's unsqueezed. Now let's proceed to what we wanted to do. We're going to predict with only random weights because we already have some architecture available, right? So we're going to say predict with random weights because we haven't done any training yet, but I want to demonstrate that we already built an architecture so we can predict. I'm going to do alt model. Remember, model is just the architecture we built here, our neural net, basically. Alt model, and we're going to feed it image batch, the 1 by 3072. This will predict something. So if we print out, it'll give us the out vector of the two values, right? And then what we need to do is, well, there are two classes in there, right? With values, we need to choose one of them. All right, so what do we need? We need to choose the one with the highest value because that represents the highest probability. That's what the model will try to learn. Which one of these classes has the highest probability of being the image? All right, so how do we do that? There's a function in Torch called Torch Max. There's many functions, but let's try this one. Torch Max, which returns the max value and index, very importantly, and index along the desired dimension in the, right? So in this case, then let's say this will return, max val, comma, index. That's what the definition says. So we're going to call torch dot max of the vector out across dimension 1. Okay, because there could be, remember, if we had fed at 64 test samples, there would be 64 answers, one for each one. So we have to say dimension 1. Does that make sense? So it gives us the results for all, but here we only have one sample, so but this is still useful. So now we just print out index, and that's your answer. Believe it or not, that's your classifier doing the work. So this would basically tell us, oh no, it's class 0 or it's class 1. What does that mean? It's either a plane or a bird. Plane or a bird. All right, so let's proceed and see if this works. Now, of course, we're giving it a correct image, but there are no, the weights haven't been trained yet, so the answer is not very meaningful at this time. And it predicted what? It predicted 1. You guys see that? So that's a result. Any questions? Oop. All right. Go ahead, please. You mean this here? We haven't used it yet. So in the model, when we created the NN object in the model, so this is just referring to the Softmax function that we're using, but it's not, we haven't used it yet. So it's just kind of a default value that's in there right now. You see that? So we haven't specified anything yet, and we haven't done any training, remember. So if we look over here, right, so we print the index here, we print the vector here, but it's referring basically to the model that, you know, it's all coming from this model where we've specified something, but we haven't done any training yet. And the backward propagation, that's done in the function, in the loop. Right, so we haven't done that yet. All right, so now you guys can build other architectures, right? So I encourage you to build other ones. You have obviously the code, so play around with different. So we only have 4 minutes left, so I'm kind of running a little bit late here. All right, so let me open up the. Let me open up GitHub. All right, so basically, you're going to have to finish this up on your own because we're out of time. Remember, next Monday is fall break, right? So no class. The following Monday is the exam. Okay, so I'll finish this up that following Monday, but I should say you should be able now to finish this. Okay, so I'll just give you a few comments. So this is the code that's posted on GitHub, right? And we've done all of this. We did all the difficult stuff today, all the new things. And basically, we got to here. Okay. What follows is several examples of different architectures. You see, this is an architecture of just a multi-layer perceptron. This is a deep learning architecture. So you can just change them around. This is the loss function that you can play with for this example. And these are just examples of testing out the loss function if you want with one image. You don't have to do this part. This is an example of how to use the train loader. So with CIFAR, so that you can actually load the data into batches of 64. So what this does is it allow you to iterate through this object and grab data now chunks of 64 instead of just chunks of 1. Does that make sense? And then what you have to do is, if you notice here, I just grab one of the models. So for instance, model 3, which is a deep neural net, I assign it to model FN, right? And then after that, it's just the stuff that we did the previous week. So this is the classifier. Remember, you have to define the learning rate. You have to define the optimizer with the learning rate, the loss function, the number of epochs, and then you have the main loop where you do the training. Does this make sense, guys? So this is what we did with linear regression. Now you just have to do it for this data set, for CIFAR10. And that's it. That'll do the training. Then this will do the testing. And then basically you'll be able to get some results. Okay, so what I suggest is, let's make this a homework as well, right? Which basically means, but as I said, I think it was a very good stopping point because all that remained was things that we had done last week, right? So you just have to now adapt your code a little bit to reflect that you're classifying. Okay, so do your best. The code is there. I was going to go over this code. You know how to load the data and everything. So as your new homework assignment, homework 3, complete this exercise. Remember, I need a report that shows, code, and in particular shows results. This should give you good results. Okay, this should give you like a good, validation losses, good predictions, etc. And then maybe grab at the end. I want you to provide a few images. Let's say a few images that were correctly classified. So show me evidence that, I classified these 3 images as birds. And by the way, they were birds. So you need to have screenshots of the birds in. You know what I'm saying? In the report, I need to see screenshots that show evidence that you completed this exercise, basically. When we come back on, so it'll be due that day, the day of the exam, and then I'll just finish it up as well. But you guys will be pretty clear on it by then. Got it? I think it's an easy homework, honestly, because we've gone over it, and as I said, the code is there. Any questions? Right, so we're out of time, unfortunately, but we'll finish this up when we're back. Don't forget, we will have our midterm exam when we come back, and next Monday is Fulbright. Any questions? Nope. All right, so don't forget the code is here, so you can just go to PyTorch, deep learning, MLP, and it is the CIFAR10 and then script. All right, so we'll stop here for today, and I'll see you guys in 2 weeks.